Assignment 168, the kid's got potential. To do this, you'll need your yellow page of half reactions. I'll refer to this commonly. Permanganate ion you worked with last week, commonly used in redox reactions. This is the purple. It reacts differently depending on whether it is used in the presence of acid. So I'm hoping you recognize H+ ions are synonymous with acid. And acid is an H+ donor. The first question should be easy. It says using your yellow page, just copy the half reaction. It does say here reduced. So I'm looking at reduction, half reactions. Trying to find permanganate on the list. And it is right here. So I'm hoping that you can copy this half reaction from your yellow page. Check back with me in a minute when you've done it. This is how the half reaction starts. You can see it's all balanced for you. It has the coefficients. These would be aqueous ions. The electrons, you notice, don't have a state. Electrons can't swim. They can't fly either. They are transferred through collisions. They're never really dissolved. The right-hand side has manganese ions, also aqueous, and 4H2O, which will be liquid. It does say now include the electrode potential. So on the chart, so on the yellow page, you'll see that here's the permanganate reaction that I'm talking about with permanganate ion and added acid, H+. It has a potential of positive 1.50 volts. We'll find that that number is very important. Since it is important, it gets written on the page. Include the electrode potential. The symbol is E with like a degree symbol called E0. 1.50 volts. Naught is another word for zero. Okay, so this is the half reaction for permanganate being reduced to Mn2+ in an acidic environment. I know it's acidic because here are the H+. The second question says now let's do a half reaction for permanganate being reduced in a basic environment with no acid, no H+ present. This reaction is not on the yellow page. Therefore, we're making it up. But here's manganese in a +7 oxidation state. On the other side, you should easily be able to verify this manganese is in a +4 oxidation state. Therefore, there is reduction, +7 to +4. Number of electrons required to get there, 3. So here's the coefficient for the electrons, which enables a reduction of manganese from +7 to +4. Now, what's left to balance? There's only one manganese, so this has to be a 1. What's the coefficient here? This is going to balance the oxygens and the hydrogens. I see a total of 4 plus 2 because of the coefficient. Oxygens on the left. Therefore, I need 6 total. Here's 2. This should be a 4. That is 4 hydrogens, which are balanced by the 4 hydrogens here. This is now a balanced half reaction. You'll notice that the potentials are quite different. The potential determines how favorable the reaction will be, how big a potential energy change there is in this process. The larger the positive, the more favorable reaction. What that means in reality is that permanganate with acid added will be able to do reactions that permanganate without acid will be unable to accomplish. We'll see that as we go through the next questions on the page. Chloride ion, it says, is a goat, meaning it can provide electrons. Mixed with permanganate ions is a wolf. You've seen it here. Permanganate ion takes electrons. If mixed in a basic environment, no reaction will occur. So here's a perfect example of what I was suggesting earlier. Let's get the half reaction for chloride ion. It comes from the yellow page. It's right here on the yellow page. It's an oxidation. It has a potential which is largely negative. Okay, so I'm just copying 2Cl minus, turned into Cl2 gas, plus 2 electrons. That's an oxidation. Potential, I'll write it as E naught, negative 1.36 volts. Now I'll imagine combining this half reaction, which is oxidation, with the half reaction above it, which is reduction. The important thing I want to look at, you know how to balance the equation by lining up the electrons. But the important thing in this example is to look at the potentials. And I hope you see here that here's a large negative potential. Here's a positive potential, but not that large. The rule is that for the reaction to occur, the overall potential of the two half reactions added together must be positive, must be greater than 0. So I'm hoping you see in this case the sum of these two will be a negative number. That means no reaction. I'm not going to write the entire half reaction, but I will write enough of it so we know what we're talking about. MnO4 plus 2H2O plus 3 electrons, blah, 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 blah. That potential is only plus write the 0, plus 0.59 volts. And here I can write the key sentence. The sum of the potentials is negative. To be specific, I can add them up and I get negative 0.77 volts. Negative potential means no reaction will occur. What this really means is that the reaction is energetically unfavorable. It's uphill. It's uphill. It's an increase in potential energy. That's unnatural. Reactions that increase potential energy don't occur naturally. That's why if you put chloride ion with permanganate and leave out the acid, nothing happens. Question 3 now says if acid is added, a reaction does occur. Write the balanced equation for the reaction. Explain why the addition of acid enables permanganate to oxidize chloride ion. Combine two half reactions here. Alright, the reason the reaction does occur must be because the potential is positive. Let's write the two half reactions again. 2Cl minus, aqueous, turns into Cl2, gas, plus 2 electrons, E naught is negative 1.36 volts. Try to line up the arrows here. I'm now taking the half reaction from the top of the page here, or if you like, directly from the yellow page here. There it is. And the reason it's going to work is because the potential of that half reaction is positive 1.50 volts. Here we go, trying to copy faithfully. It's easy to lose an ion when you do this, so try to be faithful, careful, a good accountant. Alright, those are the three reactants there. Turning into Mn2+, AQ, just one of those, 4H2O, liquid, E naught plus 1.50 volts, and I'll write my line here and try to combine the two half reactions so that the electrons balance. This is the skill you learned in class on Monday. Make this 5 and these 2 be the same number. That requires some multipliers. Try to balance this equation. Check back with me when you have balanced it. Here you can see I've added a multiplier of 5 for the top half reaction. That will be 10 electrons then. A multiplier of 2 for the bottom half reaction. That will also be 10 electrons. 2 times 5. Then I just have to be careful bringing the coefficients down into my balanced equation. You'll notice there are no electrons in the final redox reaction. The whole point was to make them cancel out. Alright, so I see 10 chloride ions. I see 2 permanganate ions. I see 16 H+. I see 5 Cl2 molecules. I see 2 manganese ions and 8 H2Os. So that is the correctly balanced equation. Total of positive 4 on the left, positive 4 on the right. The electrode potentials here do not get multiplied. So that's worth noting. Don't multiply E naughts. So that means I just add them as written. Positive 1.50, negative 1.36, positive 0.14 volts is the sum of the two. This is positive. Positive means it will work. Positive potential equals reaction works. Question number 4 says what would be observable? For most of you, you haven't thought about what does this reaction mean. Chloride ion starts aqueous, but Cl2, as it says on the yellow page, is a gas. That's an observable change. Cl2 gas bubbles would be formed. Another observable change will occur with the permanganate. You have seen that manganese in a +7 state is purple. Manganese in a +2 state is colorless. So we can write that MnO4 minus purple is reduced by gaining electrons. You saw this last week. To Mn2 plus, colorless. So a color change and bubbles would be expected from this reaction. Whenever you write a reaction, you should think about what are you expecting to happen. All right, number 5 goes back to oxidation numbers. This is from last week as well. So I'll go ahead and write in the negatives, the formal negatives in the picture, to emphasize that this is a sulfate ion. It's a -2 ion, SO4 minus 2. Might as well write it. You've seen this many times. What are the oxidation numbers? -2 for each oxygen, leaving the sulfur to be +6. You might think +8, but that would make the sum be 0. Want the sum to be equal to the charge of the ion, so the sum should be -2. So this sulfur is in a +6 oxidation state. It's not charged. It's an oxidation number. It's an oxidation state. Question 6. You should try this before I show you. Use some skills similar to what we did up here, right? Similar to what we did up here in question 1b. All right, here we go. This is how you should have done it. That sulfur is in a +6 state. That's what we already determined prior. How about this sulfur on the right? It's in a +4 state. That indicates reduction by 2 electrons. The rest of it is balanced by inspection. There are 4 oxygens here. There are 3 plus 1. That has to be a 1. 2 hydrogens mean 2 hydrogens. So that's fairly easy to balance. You'll notice the potential is written. That's important. That determines how favorable this process is. This process is pretty favorable. But by itself, this means nothing. You'd have to combine it with a second half reaction to determine can that reaction actually occur. Number 7 says, write a correctly balanced half reaction for sulfite ion. Sulfite ion, SO3, being oxidized to form sulfate ion. Going back to sulfate. There's a hint here. It says, if you look at what you did in problem 6, and what is this nonsense? This nonsense is just think backwards. Try to do this before I show you. What this means is here's sulfite ion, and here's sulfate ion. So if you just write it in the other direction, you have the answer to the question. Sulfite ion plus 1H2O can become sulfate ion plus 2H plus 2 electrons. Let's write the phases. That helps you figure out what this should look like. Again, the electrons are not aqueous, they don't swim, they're just transferred to something. Someone will have to receive these electrons. Potential, when you turn the half reaction around, the potential changes its sign. You've seen this on the yellow page numerous times. If you switch it around, the sign becomes the opposite. All right, last question, not a lot of space there. If sulfite ion, here's sulfite ion right there, boom, is mixed with permanganate ion in a basic environment, that's this half reaction up here, would a reaction occur? So here I've cut it out and put it down here. Here I've cut out the permanganate half reaction to make it easy to line them up and see would these react. Here's an oxidation. Here's a reduction. That's important. You need both reduction and oxidation to have redox. And then you look at the potentials. Will these react? The potential is overall positive. So the answer is yes. A reaction will occur when you react permanganate and sulfite ion without any acid. The potential is high enough to be positive. If the permanganate were acidified, then the reaction is also positive. So in this case, sulfite ion can react with permanganate in an acidic environment or in a non-acidic environment. There will be a reaction in either case. Products will be different though. In the basic environment, we expect to see MnO2. In the acidic environment, we expect to see Mn2+. Those are different products. Also have some different products here. So what you write on the paper is this. SO3, 2 minus, that's sulfite. Let's write the word. Can react with permanganate. With or without added acid because let me not get ahead of myself, because the potential is positive in either case. The potential is positive in either case. Good. All right, that's the lesson.